Okay, here are our quiz problems. Sure. Have all that on the board. You have a p of x function, a q of x function, very similar functions, both polynomials, but of different degree. And then we have an r of x function. Let's work first. From what I see, I think I want to start with the q of x function, so I can explain something about that. Y equals x plus 2 squared times x plus 7. Okay, well, first thing, let's start by finding the degree of this polynomial. We're going to expand. We haven't done this before. But I will say, when it's expanded, the leading term is x cubed. So viewed from far away, graph looks like the x cubed shape. It has the x cubed shape. So here is, it's got a coordinate axis, and here's the x cubed shape. Now, all the wiggles, as I call them, all the zeros I'll use a terminology for more advanced math, but we understand it. All zeros are in a small neighborhood of the origin. Okay. Matter of fact, all intercepts are in a small neighborhood of the origin. So now we want to look at this small neighborhood. So I've got that indicated by a blue circle. So I'm going to draw a blue graph to indicate that we're now looking at this tiny neighborhood here. Okay. And we see that the zeros occur when y equals 0. And you want to write that out so that you're sure, not just out of habit, set that equal to 0, set that equal to 0, and there are your zeros. That's quick, but you have to understand you're letting y equal 0. So you want to write that little indication of what you do so you remember what it is you're actually doing. Okay, you get this, and you get a solution. Now, x plus 2 squared equals 0 if x plus 2 is the square root of 0, which is 0. And you get then x equals negative 2. And then x plus 7 equals 0. Well, you can solve that. You go through the steps. You're going to get x equals negative 7. So if you had your zeros on the right-hand side of the axis, you need to write this out more carefully when you do it. And if you do that for half a dozen problems, you'll lock it in. And then when you're going to be tested over it, just take a quick review to remind yourself. You might forget it, but a quick review before the test if you've been writing it out in detail, will remind you of what you've been doing. And you want to remind yourself what you're doing every time you do it when you're learning it. All right. So anyhow, we're going to let x equals -7 ohm, let's say here, and x equals -2. Here. So now we have these 2 points. The graph has to go through these points. Now, the x equals 2, 0 is of degree 2 because x plus 2 is being squared. In other words, the 0 near x equals -2. This is just like the x squared function shifted left 2 units. And we need to understand that. Now, it's shifted left and also extremely stretched because of the, well, not that extremely stretched, because of the x plus 7, but we know that it's going to act like an x plus 2 squared. Now, it could be opening upward or opening downward, but it's going to be a parabola. It might be like this. I'm drawing that lightly. Can you see that? I just very lightly drew a parabola just to indicate that it's going to be either like this or like this in the immediate vicinity of this point. Okay? Now, as you move away from this point, that apparent parabola is going to get lopsided, and pretty soon it's not even going to be anything like a parabola. But close to this point, it's going to be very much like a parabola. Okay? That's because of degree 2. It's because near x equals -2, x plus 7 is equal to 5, right? And if you stay close to x equals -2, this is going to stay close to 5. This is going to be a lot like 5 times x plus 2 squared. X plus 2 squared function stretched by a factor of 5. All right. Well, let's see how it's going to work out now. We also have a y-intercept. Again, even though you can see this very quickly once you get in the habit of doing it, if you don't write out what you're doing, you're not going to remember it very well. At least not as well as you're capable of remembering. Well, that's 4 times 7, which is 28. So we're going to draw a horizontal line here and label it y equals 28. So now we can put a scale on the x-axis and we can put a scale on the y-axis if we need it. Right now, we're just trying to graph the function. What else do we know? We know that the thing is going to go down as we go to the left, because this is what it's got to look like if you zoom way back on it. It can't go through the x-axis unless x is equal to -2 or -7. Any other value of x, this is not going to be 0, and this is not going to be 0, so this times this can't be 0. All right, so we've got to be below the axis to the left of x equals -7, because we know we're below the axis if we go far enough to the left. It's obvious from the behavior of the cubic function. So we're going to come up through this 0 here. And then we got to turn around to come back to this 0. And when we do, it's going to be like a parabola. Okay. And then we're going to move on up through this point. I made that a little too steep, but, and then we're off on this part of the picture. we know that as we continue to the right, we're going to have to go up rapidly. Okay? So there's our graph. And it doesn't hurt to reinforce things by saying this is -7, 0. This is -2, 0. And this is 0, 28. So that all the calculations and what we've labeled on the graph and the nature of this graph go together to explain what we have here. Okay? Now, I said we we're going to expand this just to show why you have an x cubed. So I'm going to go ahead and do that. We expand this. Okay, well, that equals x plus 2 times x plus 2 times x plus 7. Now I'm going to isolate the x plus 2 times x plus 2. X plus 2 times x plus 2 is x times x plus 2. So the x multiplies the x plus 2, but the plus 2 also multiplies the x plus 2. Now it's all this multiplied by x plus 7. I didn't leave myself enough room, but we're used to that, I'm afraid. Okay? So the x plus 7 is still there, but we're kind of focusing on x plus 2 multiplied by x plus 2. Well, x times x is x squared. X times 2 is 2x. 2 times x is 2x. 2 times 2 is 4. And we've got x squared plus 4x plus 4. And naturally, I didn't write my x plus 7 in, and I don't have room for it. Well, there it is. It's a little bit small. Here it is. It's a little bit obscured, but it's just inherited. The x plus 7 is inherited at every step. We've done what's in parentheses, and we've gotten this, and then it's multiplied by x plus 7. Okay? And what's that equal? Well, that equals x squared times x plus 7 plus 4x times x plus 7 plus 4 times x plus 7. I'm working with even less room, but we multiply the x squared by x plus 7. X squared times x plus, I'll just say 7x squared. X squared times 7 is the same as 7 times x squared. And then it's going to be 4x times x plus 4x times 7. And then it's going to be 4 times x plus 4 times 7. Well, x squared times x is x cubed. 7 times x squared is 7x squared. 4 times x times 4x times x is 4x squared. 4x times 7, 4 times 7 is 28, and we've got the x. And then 4x is 4x, and 4 times 7 is 28. Now you just keep your wits about you and just do everything one step at a time and use the distributive law appropriately. And you end up with x cubed. 7x squared and 4x squared is 11x squared. 28x plus 4x is 32x. And then we have plus 28. Okay. Now what you have to understand is if x is really big, it's much, much bigger than any of this stuff or all of this stuff together. If x is 100, x cubed is 1,000,000. X squared is 10,000. 11 times that is 110,000, which is a little over a tenth as big as x cubed. Okay. And the rest of this doesn't amount to a hill of beans compared to 1,000,000. If x is 1,000, this is 1,000,000,000. And this is 11 million, which is around 1% of a billion. Okay. And the bigger this gets, the smaller the rest of this gets as a percent of x cubed. So when you zoom way back, if x is a billion right here, or a million right here, sorry, even 1,000 right here. If x is 1,000 right here, then the value of this function and the value of this function, you're not going to be able to see a difference. You don't see a difference until you get close to this area here. When you get close to this area here, yeah, it wiggles a little bit. But then for too long, it practically joins up almost exactly with the x cubed function. Okay? Now I kind of lied because you got that plus 28. So kind of like x cubed plus 28. And there are other little variations. But 28 on the y scale compared to a billion, you can't even see it. Maybe with a decent microscope. Okay? Or a very, very big graph, a couple miles high. Okay? Does that have to make sense? That's pretty much the entire picture of what you have to do to graph a polynomial function. So going into a little less detail, let's figure out the graph of this one. What do I have to do next? Okay. So I'm going to take both of these. And I got too many of them. Got to make these a little heavier so I know for sure when I have too many. Okay. Now, the next function we had was p of x equals, it's a cube and a linear, but x minus 1 cubed times x plus 4. And it's y equals, because when we do the graph, we're going to graph y versus x. P of x is just the name of this function. X-intercept from y equals 0. The x-intercepts are at the x values. This is an abbreviation of the word solutions. Okay, so it's solutions of this equation. And this is cubed, not squared. Okay, so this gives us x minus 1 cubed equals 0, or x plus 4 equals 0. So x plus 4 equals 0 gives the obvious solution, x equals negative 4. Okay. And we get x equals 1. Now we can see that just looking at this. But sometimes what you have in the parentheses is more complicated than just x plus this or x minus that. You've seen that in the homework. I'm keeping it simple, but you get, if you write this out, you get a linear equation here and a cubic equation here that you're solving for zero, okay? So it's very easy to solve. What we want to look here at here is the multiplicity of this one is 3 because of the cube. Multiplicity is 1. So if we begin to sketch the graph, we have x equals 4, x equals negative 4. Let's say here, and x equals 1 here. The y-intercept so you get y equals 0 minus 1 cubed times 0 plus 4. And that equals negative 4. So you have a y-intercept here at y equals negative 4. So we have these 3 points. And I'm not going to label them just now, because I want to draw the graph. And if I label them before I draw the curve's probably going to go through one of my labels. I keep my labels clear of my curve if I draw the curve first. Now, what's the curve going to look like overall? Okay, well, find that the leading term is x to the 4th. When you expand this is cubed. You multiply x minus 1 times x minus 1, you're going to get an x minus 1 squared. And multiply that by an x minus 1, well, you multiply that x squared by another x. And then multiply by x plus 4, you got an x cubed now. You're going to multiply that by this x, and you're going to get an x to the 4th. Now, you should be able to expand that by the distributive law, but that's what you get. And you confirm that the leading term is x to the 4th. Now, if there's a number out in front here, like 5, then the leading term would be 5x to the 4th. It still looks like an x to the 4th. So again, right here are the details of the wiggles. Over here, we zoom way back, and we get something that looks like the x to the 4th. And then you might have some wiggles. Whatever wiggles there are will be in here. So that this, I drew it in blue before, I'm just going to draw that circle. If we enlarge this circle, and on the big scale, the circle's actually much tinier than that. We enlarge this tiny circle, and here's what we see within that circle. We see x-intercepts here and here, and a y-intercept here. We have a 0 of degree 3 at this point. Okay, so this is going to be of degree 3. this is going to be linear or degree 1. Meaning, well, we can see what's going to happen. Long run, it's going to go up on this side and it's going to go up on this side. That's what this function tells us. So long run, you understand that the long run is easiest to do if you just know what the graph of the power function looks like. An even power function is always going to look like this. An odd power function is either going to be linear straight through, or it's going to do this, like a cubic function. The higher the power, the flatter it gets near the origin. Okay? If you know all that and put it together, then you can draw beautiful graphs. Especially in that thing you write on. Picking out one person here. Has a neat little tablet type thing. Comes out beautifully. Okay, so how do we do this? Well, we got to come down from here and go and at least touch this 0. Now, if this is a degree 2 0, we might come down and turn around, okay? But it's a degree 1 0, so it means we're just gonna, if we zoom in very close to this point, it's gonna just look straight. We're not gonna be able to detect any curve, but there is some curvature. So it's gonna come down through here. Now, what's it gonna do? It's gonna have to curve because it's gotta go through this point. It can't go back through the x-axis because any value of x other than 1 or -4 won't make this 0. That's another thing we got to be sure we understand. So we come down through here. This is kind of a boring graph. We just come down through here, and maybe we go through this point and then turn up and go here. Now, actually, we probably come down a little lower than this point and come up. So I didn't do a very good job of that. There's no reason to expect that this will be the lowest point of the graph. And that's kind of important. So let me redraw that a little more generally. Okay, so we come down to here. And it comes down lower than this point and probably comes back up like this. Probably doesn't look exactly like that either. This almost looks like a parabola, but it gets way too steep out here to be a parabola. Okay, does that make sense? You want to sort that out. Remember that there's a pretty decent transcript that goes with the video. It's pretty decent. I don't have time to edit these things because of other demands in my time. I'm spread too thin, and that's unfortunate. But the editing would take me, 10 hours a week for my classes, and I just don't have it. Still, you can read through the words and see everything that I've said here, or you can just listen to this part of the video or view this part of the video. If you get all that down, it's very easy to do this with any factored polynomial. Now, there's more to it, and open math tells you more, and you're going to see more in pre-calculus. But this is all we're going to do in the support course. We're going to understand this much, okay? And then whatever else you can pick up from the open math. So the homework I've seen on this generally looks pretty good. Oh, gee, I screwed this graph completely. Said this is degree 3. Does that look like degree 3? Heck no. Okay, so we got to kind of modify this. Okay, now we got to come down through here. When we come up, then we're going to have to be able to level off when we go through the 0 here. So that means we're probably going to have to come down even further. So we can come up pretty steep. So we got room to level off. before we continue on. Okay, I apologize for overlooking this thing that I wrote here, because that's exactly what I'm trying to illustrate here, because that's what I saw on a lot of papers. I saw that people were not respecting that degree 3. So get a little respect. Okay. Do what I do, at least after I correct my error. Okay. Again, get that much down, and you're in good shape to understand what you're going to see in pre-calculus here in a short time, like then an hour. Okay. And of course, we went over this last week, so you've got your feet wet, so you're going to be ready to understand a little more detail. Now, the Q of X thing, or the R of X. Now, let me just draw Q of X. That's one we did originally, X plus 2 and X plus 7. Remember that graph? Had a 0 at -7, had a 0 at 2, -2, and had a y-intercept of 28. So, and the graph ended up then in something like this, a little funny over there. And we have the graph of this function. Now, what about R of X equals P of X over Q of X? Well, we write out the formula. That's going to be X minus 1 cubed times X plus 4. And the denominator X plus 2 squared times X plus 7. Okay, zeros. Let's find x-intercepts. And the numerator is 0. So the x-intercepts occur. And I've got 3 dots here. The same thing we did here. I already did it over here. But you would go through all this, but you wouldn't do the graph. I'll show you what you would do. You get that occur x equals -1, and you list the degree. That's going to be degree 1. So if we're drawing our graph, we have so I need to draw this graph a little further to the right, because we want to be able to see what happens to the left of x equals 7. There's more stuff going on to the left than there is to the right because of the x equals -7, 0 of the denominator, but we haven't talked about that yet. Okay, so at x equals -4, we'll say that's here. X equals 1, we'll say that's here. My scale isn't great, but that's going to be okay. Okay, and this is going to be degree 3. I think I'm safe labeling that here. This is going to be degree 1. I don't want to label that just yet. I don't know what I might get in the way of. Okay. Y-intercept is when x equals 0. So it's at y equals 0 minus 1 cubed times 0 plus 4 over 0 plus 2 times 0 plus 7. And you might not be able to read that, but you know how to plug in 0. 0 minus 1 cubed is negative 1. Multiply that by 4, you get negative 4. 2 times 7 is 14. Or negative 2/7. So that y-intercept is not going to be at all to scale. Okay, here's the line y equals negative 2/7, very close to the origin. Okay, now denominator is 0. When x equals negative 2, which is of degree 2, x equals negative 7, degree 1. And we note that the numerator is not 0 when the denominator is 0. And that's important. If the numerator was 0 when the denominator was also 0, we couldn't say that as you approach this x value or approach this x value, the thing blows up. Because as x gets closer and closer to negative 2, this gets closer and closer to 0. Okay? This means your denominator gets closer and closer to 0. The numerator doesn't get closer and closer to 0. So the denominator goes into the numerator more and more and more times the closer x gets to negative 2. Which means that this thing gets huge, approaches infinity, or maybe negative infinity, or maybe infinity on one side of the x equals negative 2 line, negative infinity on the other side. Well, let's go ahead and draw the x equals negative 2 line. I'm going to draw that in a different color. And then I'm going to draw my x equals negative 7 line. Okay, these lines are going to be vertical asymptotes. These points are simply going to be points on the graph, and so is, almost put the point in the wrong place, the y-intercept. Okay? Now the y-intercept again is very close to 0, but I'm kind of exaggerating how far it really is. All right, just so we can see it on the graph. Now near x equals negative 7, The graph shape is like 1 over x plus 7. Well, 1 over x is your basic reciprocal graph, positive in the first quadrant, negative in the third quadrant, right? So we know what that graph looks like. So the graph is going to look something like that here. We don't know whether it's going to be like this. That's one possibility. But there's another possibility. It might be like this. It'll be this or this. We don't know yet. We could test that. It depends on whether the rest of the function is positive or negative, near negative 7. Not going to worry too much about that. We'll figure it out in a little different way. Okay. Near x equals negative 2, it's like 1 over x plus 2 squared. Now that would end up looking something like this. And since the graph has to go through this point, it's going to be like this. Okay. Now the graph of 1 over x plus 2 squared is a lot like the reciprocal function, except you're squaring this. So it's going to be kind of steeper, and it's going to be positive on both sides of the y-axis, the asymptote. So in any case, we know this part of the graph. So I'm going to actually fill that in with a fairly prominent color. It's got to go through this point. So it's going to be like this. Now I'm out of board space. So I'm going to space over here and say that the long run of r of x, which is p of x over q of x, which equals that's like, remember that this x minus 1 cubed times x plus 4 has an x to the fourth in it, and that's the leading term. If you multiply this out, you get an x squared from x plus 2 squared, you get an x here. So it's like x to the fourth over x cubed, which is just x. What's the graph of just plain old x look like? It's like y equals x, except that you have this region in here, and I'm going to make this region, that's a very thin region, bounded by a vertical strip, and there are wiggles and asymptotes in here, in this region. And that's the region we're looking at here. We're in that blue region. I'm not going to color it blue because obvious reasons. So we've figured out, here's one of your asymptotes. It's just like a reciprocal x plus 2 squared, but it's flipped upside down because all this other stuff, other than the x plus 2 squared, turns out to be negative at this point. Now, what happens at this asymptote? If the overall behavior is like the y equals x function. Now, I've got a problem with scale here. I'm just going to say, I'm exaggerating things, and this is not exact. This is kind of like y equals x. Because the y equals x is below the x-axis here, and you can't cross the x-axis until you get in to the wiggle and asymptote region. The graph has to approach this asymptote like so. It's close to the y equals x line, and actually it isn't the y equals x line, but we'll see a little bit more of that. It's going to be like this down here, which means, remember, it's like a reciprocal function. Reciprocal function is down on one side, up on the other side. So on this side, it's going to be up here. It's going to come down here through this zero and join up nicely to make this asymptote. Okay? Now, it's then on the other side of the y-intercept, it's going to go through here, but it's going to approach that y equals x line as an asymptote. So that's kind of what the graph looks like. But I'm lying to you a little bit. Actually, if you want to figure out what this line is, you have to divide this denominator into this numerator. So I haven't expanded this denominator. I did expand the numerator. I think we can expand the denominator pretty quickly. We ended up with x cubed and plus 28 down here. But we had a bunch of other stuff that I don't remember, and it's on this board, so all I have to do is look. 11x squared and 32x. Now, x plus 2 squared times x plus 7, I'll just scratch that down here. You can use the distributive law, x plus 2 times x plus 2. You get x squared plus 4x plus 4. That's multiplied by x plus 7. Then you multiply everything here by x plus 7. And I'll put some dots here, but you're going to end up with x cubed. And then you're going to have 28x from this and 4x from this, 32x. Let's make sure that I'm doing what I did before. This is starting to look awfully. Oh, heck. Okay, I was ignorant. I was looking at. Divide the numerator by the denominator. So the denominator is your x cubed plus 32x. It's not 32x. It's 4x squared and 7x. 11x squared plus 32x. Not 32x, is it? Yeah, it is. Okay. This is your denominator. So you're going to divide x cubed plus 11x squared plus 32x plus 28. Doggone, I didn't leave myself enough room again. Okay, well, it's a little sloppy, but there it is. That has to divide into what we get if we expand this. Now, if we expand this, we're going to get x cubed minus 3x squared I've got to reverse signs. Yeah, okay. Just being ignorant the way I'm looking at it. Plus 3x minus 1. And that's multiplied by x plus 4. And that gives us x to the 4th. And then it's minus 3x cubed plus 4x cubed. So that's plus x cubed. And it's plus 3x squared and minus 12x squared, which is minus 9x squared. You don't have to follow this. And then it's 3x times 4, which is 12x minus 1, which is plus 11x minus 4. If I did that right, we have this long division. How do we divide this? X cubed goes into x to the 4th, x times. Multiply x by all this, we're going to get x to the 4th plus 11x cubed plus 32x squared plus 28x. We've got to subtract this from this. That's just like what you do with any long division. Okay? It's just a little bit longer, but it turns out to be a shorter calculation. So we put little minus signs on all of these. And we get negative 8x cubed. That's not negative 10x cubed minus 41x squared plus 39x plus 4. And we can divide this into this and we get minus 10. And then we get negative 10x cubed plus 111x squared plus 320x plus 280. And you don't need to worry about those details. It's easy to write it down. Make sure we change all the signs here. That'll become a plus. That's a minus. That'll be a minus. That'll be a minus. And we're going to end up with, I think, negative 152x squared minus 281x minus 276. Now, x cubed is bigger than x squared, so it's going to be x minus 10 plus negative 152x squared minus 281x minus 276 over x cubed plus 11x squared plus 32x plus 28. Now, I went through that kind of fast because the steps are really straightforward. Just got to copy them down, do the arithmetic right, and chances are I made a mistake. The point is, this has an x squared term, leading term on top. This has an x cubed. Pretty soon that x cubed is going to be so big that you don't care about that negative 152x squared. This thing is going to approach 0. If x is 1,000, then this is going to be a pretty small fraction, like 1/6 or something. Okay, and the bigger x gets, the smaller that gets. The point then is that this line really should be y equals x minus 10. Okay? So really it's going to be somewhat lower than this. And when it comes up through here, it's going to have to descend to hit the line. Okay? So this should be y equals x minus 10. So that line should be lower, and that's going to change the shape of the curve a little bit. This is called a slant asymptote. You've seen that, I think. And that's what's going on with a slant asymptote. Now, this is gets pretty hairy with all the terms and everything. But there's nothing unfamiliar about it if you understand how to do long division. Okay. If you do a long division and the exponent here is 1 greater than the exponent here, you're going to get an x here. And then depending what the other numbers are, you're going to get another number here. It's going to be a linear function like x minus 10 or x plus 40, something like that. And that's what you're going to approach. Okay. Okay, so that's time. We're 1 minute over. Apologize for taking a minute out of your life. Blame it on Zoom. I'll blame it on my computer. Okay. Which went to sleep.